Hello, so a while ago someone asked me, in this equation for fluids, pressure is equal to force over area. So this person asked me, why is it that this force is perpendicular to the area A on which it acts, in the definition of pressure? So I'm going to demonstrate this conceptually, why that force has to be perpendicular. So let's imagine we have here a swimmer under the water. We know that the swimmer is going to feel forces on all directions, at all points, on the swimmer's surface area, due to the weight of the fluid exerting a force on him. Okay, so let's zoom in on this guy just for a second. And let's say we're zooming in on the surface, or let's say the top of this person's head. What we see here that all these forces have to be perpendicular to the surface area A over here. Or in this case, the top of the person's head that we zoomed in on. Now let me try to prove this fact. Let's look at a force that isn't exactly perpendicular to the surface area. So let's call this force F. Now remember, all forces are just vector quantities, so any vector quantity can be decomposed into its x and y component. Now looking at this, we see that f of x is parallel to the surface area A. Therefore, it is not being exerted on the surface area A. Meanwhile, we see that Fy is actually directly perpendicular to surface area A. Hence, this is the force or component of the force that's exerted on surface area A. So let's try to prove this by looking at a similar problem in mechanics. So suppose you have a mass m sitting on the table, and this mass neither moves up nor down as a result of being pulled by some force Fp at a certain angle. So what we do know is, again, force is a vector quantity, so it can be decomposed into parts. So I'll call the horizontal component Fpx, the vertical component Fpy, and what we see from this example here, if the box is neither moving up nor down, we see that Fpx is the only component of the force that moves the box, or rather in this case, it is the only component of the force that drags the mass m along the floor. Now, let's try to extend this concept and contest this idea further. So let's again draw our usual surface area A. right? And let's say we're looking at the top of the person's head. We see that there are forces on the sides, and there's a force directly perpendicular to the top of the head, or the surface area A. So here, again, let's call this one F1, F2, F3. We recognize that these are all forces, so each of these forces can be decomposed into their parts. So for F1, there's F1x, and then F1y. Likewise, same thing for force 2, only the difference is here F2 only has a perpendicular component. Same thing over here with our third force. We see, okay, this becomes F3x, this one becomes F3y. Alright, now let's pay some close attention to F1 and F3. We see that F1 is pretty much the force or weight of the fluid a little over the left edge of area A. Likewise, the same thing goes for F3, which is the weight of the fluid a little over the right edge of area A. So, if we say that F1 and F3 are equal, meaning there is an equal amount of fluid or weight of the fluid on each side, acting on the sides, the right edge and the left edge of surface area A, then we can clearly see that the horizontal components are equal to each other and they cancel each other out because they're in opposing directions. However, we should also further note that F1y and F3y, though their directions are perpendicular to surface area A, they will not contribute to the pressure on surface area A, because look at the positions where F3 and F1 start. They are actually perpendicular but not being exerted against surface area A, if we pay particularly close attention to them. They actually miss that surface area A. So that's another important point to note. Now it would be a different story if surface area A was slightly curved. Then there may be a chance that some component of those perpendicular components would actually be exerted on surface area A. But again, it's only the perpendicular components of the force that will actually be exerted on an area, following the definition of pressure. Now, this concept is similar to this idea over here. Again, let's take a mass m here, and we have a force that's pulling that same object again. Here we have Fpy, and then we have Fpx. What we recognize is here there is a normal force that is equal and opposite to the force of gravity against this mass m, where this mass neither moves up nor down. So speaking of this example, we'll also talk about the forces underneath the person. Now the free body diagram is such that the normal force plus Fpy, the force pulling up the person, minus the force of gravity pulling down the person is equal to 0 if this object is neither moving up nor down. Therefore, we can conclude that only the force Fpx acts along the x direction to drag the block across the floor. So what can we take away from all of this? Well, we can take away the following from all of this. Basically, all the forces acting on a submerged object is exerted by the weight of the surrounding fluid. And those forces will be perpendicular to the surface area A on which they are exerted. And this ratio is defined as pressure.